Okay, very good. Let us start then. Today we have Alexandre Homrich talking about structure constants in n equals 4 super bills and separation of variables. So thank you again, Alexandre, for accepting our invitation, and please go ahead.
Yeah, thanks for the invite. Yeah, so I'll be talking today about this work that came out recently with my collaborators, Carlos and Pedro. And when connecting to Zoom, I realized I forgot to add references to the slides. So I apologize for that, but I'll not say anything that's not in the paper, and the paper has all references you might need. But having made this disclaimer, so it's been a major goal for a while in the QFT community to have a complete solution of CFT in D greater than 2. And by complete solution, I mean a complete specification of all the local correlators in the theory. So arbitrary correlation function of local operators. Now, a major candidate for the first CFT for which this could be realized is planar n equals 4 super Mills. The reason for that is that through the CFT correspondence, the correlators of local operators in n equals 4 super Mills are governed by the dynamics of the dual worldsheet. And the dynamics of the dual worldsheet is integrable. And you can therefore use integrability methods to explore the dynamics of the 4D conformal field theory. Now, these words can be shown to be actually very realistic because, for instance, the first part of the problem of the complete solution of planar n equals 4 is done. So the spectrum of the local operators in the theory can be numerically computed for arbitrary operator at arbitrary value of the top coupling by means of the so-called quantum spectral curve. Now, the quantum spectral curve has as its key element the so-called Q functions, which I will describe soon. And it's only when the spectrum problem is described in terms of these objects, the so-called Q functions, that the simplicity of the spectrum problem is maximized, and we actually have also optimal computational efficiency, so that you can actually compute the spectrum for arbitrary state operator and the arbitrary value of the coupling. Having said that, it's very natural to look for a framework for the quantum structure constants in n equals 4 super Mills based on these Q functions. This will be the first step for a complete solution of planar n equals 4 for higher point correlators. So the goal of this talk is to develop such a framework in the simplest sectors of the theory at weak value of the coupling. After doing that, I will compare what we achieved with existing methods for structure constants in n equals 4 super Mills and describe a bit of why we are so excited about this result. Finally, I'll conclude with a summary of what we achieved and discuss some future directions. Is everything clear so far?
Mm-hmm.
Okay, so what are these Q functions after all? So in the simplest integrable models, these are some polynomials whose nodes capture the excitations of the state. That's described by the Q function. So this should be familiar to every one of you, at least in one example. The example is the quantum harmonic oscillator. So recall that the eigenstates of the quantum harmonic oscillator in position space are given by the Gaussian dressed by these Hermite polynomials. And these Hermite polynomials, if you plot them, they're essentially this. So you see that the vacuum state has no nodes. And then as you climb up into states with more and more excitations, you have more and more nodes. And the position of these nodes are essentially fixed by the wave function through Schrodinger's equation. So you can think of Schrodinger equation as a quantization condition for the position of these nodes of the wave function of the harmonic oscillator, or the nodes of these polynomials. So the Hermite polynomials are the Q functions of the quantum harmonic oscillator. So in general, states are described by Q functions. And in the context of n equals 4 super Mills by states, I really mean local operators. And therefore, what we are after are a map from structure constants to Q function, or better saying, from Q functions to structure constants. So we look for a functional that eats Q functions and outputs the 3-point functions. Now, to start with, let's look for a simpler functional that will prove useful in the structure constant problem later, which is a bilinear that eats instead 2 Q functions. And if they describe the same state, they provide a normalization. Otherwise, they give 0. Okay? To achieve that, well, let's first restrict ourselves to some of the simplest operators in the theory, which are operators in the so-called SL2 sector of the gauge theory, which are operators of the schematic form. They're single trace operators with Z scalar fields, with L scalar fields, which are labeled by Z, and J covariant derivatives, which are labeled by D, plus permutations. So permutations, I mean, permuting the covariant derivatives and the Z fields inside the trace. In particular, let us restrict us first to twist 2 operators. So L equals 2, the lowest Regge trajectory. So operators in this family are described by Q functions, which again are polynomials whose roots are labeled by uj. For spin j, they have j roots. And physically, these roots, they essentially describe the momenta or these covariant derivatives inside the chain of Z fields that this trace describes. Okay. And as in the quantum harmonic oscillator, these roots are quantized. Here we have, in this case, they're quantized by the so-called Baxter equation, which is a finite difference equation given here. Okay. So let's digest this equation a little bit. So we define this B operator, which is essentially defined by the left-hand side of the equation. And then this essentially an eigenvalue equation for this B operator, for which we must solve both for the eigenfunction, which is the Baxter polynomial Q, and the eigenvalue T, which is the transfer matrix. The eigenvalue, of course, depends on the operator. Therefore, I use this label 1 here. Now you see, the left-hand side, the Q is a polynomial of degree S. Sorry, J. J is a spin. Sometimes I'll say S because well, it's natural. And then it's multiplied by a polynomial of degree 2 in this case. And therefore, by matching the degrees of the polynomials on the right-hand side, we see that T is a polynomial of degree 2. And then if you look at the asymptotics of the two sides by looking at the highest powers in U, you see that the first coefficient of T is fixed to be 2, U squared. And if you look at subleading asymptotics of this equation, which I do not describe here in detail, but you can do it yourself later, and you'll find out that this B coefficient is actually 0. So really, this transfer matrix, despite being a polynomial, really contains a single degree of freedom, which we call C1, and which is a function of the state. Okay. Now, I remind that our goal here is to construct these bilinear pairings for 2 solutions of this equation. That is an orthonormal pairing. So to do that, let's consider the following object. Let's consider the B operator acting on the first solution Q1 times Q2 minus Q1 with the B operator acting on Q2. Okay. You see, since Q1 and Q2 are eigenvalues of this equation, we can evaluate this through the right-hand side and express this as Q1 times Q2 times the difference of the eigenvalues, right? Now, let's integrate this equation along the real line against some measure mu. Okay. Now, note, B is state independent. Therefore, suppose that B is a self-adjoint with respect to this measure mu. If it were self-adjoint, then we could move the action of B on operator 1 to operator 2 and rewrite the left-hand side in this way. And this, of course, is 0 since B cancels. But on the other hand, it's also equal to the right-hand side. And if the operators Q1 and Q2 are distinct, then their eigenvalues will also be generically distinct. And therefore, since this is non-zero, we must have that this bilinear integral is 0. Of course, this breaks down if the state is Q1 equal to Q2, because then we have a trivial 0 from the eigenvalues. And therefore, we see that provided we can find a measure for which the Baxter operator is self-adjoint, then we'll have constructed the bilinear we were after. Okay? Is the logic here clear?
I think it is.
Okay, so we want to make the B operator self-adjoint with respect to the measure mu. So let's consider one of the terms of the left-hand side of the integral we were considering in more detail. So in explicit form, we have this object. So I have the integral of the left-hand side of the Baxter equation. And now let's perform a contour manipulation. Let's shift the first term here down by I, and the second term here up by I. Now, let's ignore for a second possible singularities along the contour deformation. Assuming no singularities, what we find is that first, of course, Q1 becomes integrated along the real line. And then you see that suppose that the measure is I-periodic, so that here I can replace U of minus I by mu of U. And similar here. Then, essentially what happens is that this term is the action of the Baxter operator on Q2. It becomes this term here acting on Q2. And this one becomes this. So essentially, by doing this contour manipulation, we managed to shift the B action from operator 1 to operator 2. So we see that provided we can both ignore possible singularities along the contour, and provided the measure is periodic with period I, we make B self-adjoint. So what are I-periodic functions? I-periodic functions are functions of this form, perhaps times some hyperbolic tangent, which could be considered, but it will not be needed. And then you see, a measure of this form would be aperiodic, but it has an obvious problem, which is that for k positive, this measure blows up exponentially. This measure is being integrated against polynomials, and therefore this would not be a convergent integral. So from convergence requirement, we must restrict ourselves to k negative. Okay. But now for k negative, we have a different issue, which is that 1 over cosh has simple poles at plus minus I over 2, which are along the path of the formation we considered, right? So these deformations pass through minus I over 2, and this one passes through plus I over 2. So for arbitrary negative k, we would have problems with poles. However, note that we have zeros in the integrand precisely at this position. So we have double zeros at minus I over 2 for the first term, and double zeros at plus I over 2 for the second term. This means that if the measure has at most double poles at these positions, then I do not capture any singularity as I deform the contour. So essentially, this fixes the measure completely. So k must be 1, so that I have at most double poles. So in this way, we managed to construct the bilinear pair we were after. We just integrate the 2q functions against this universal measure 1 over cosh squared. Okay. Now, any questions so far?
Yeah, sorry, just one. Why is 1 over cosh excluded? It's allowed from the poles, right?
Sorry, I could not hear you well.
Can you say?
The question was, why is 1 over cosh excluded? It's not.
So what?
So, I don't know. Because the measure is the cost minus 2, cost minus 2. So,
Okay. The question is why you need double pole.
not so, like,
1 over cosh.
So why not 1 over cosh instead of 1 over cosh squared?
Yeah, that was the question.
Yeah. So 1 over cosh is not aperiodic, right? It's anti-periodic. That's why I'm restricting myself to even powers of cosh here.
Yeah. Okay. Right. Okay. Thank you.
So this is the property I want that restricts cosh to have an even power. Okay.
Yeah. Thank you. Thank you.
Yeah, I tried this talk yesterday, and it took me over an hour. But by the speed I'm going now, it's going to be finished in 40 minutes or less. So please ask me questions. Okay. So the question is, why are we considering these bilinear pairings? Well, before me commenting that, let me make a comment, which is that what we described so far was for operators of twist 2, right? So, for example, this power 2 here is very much related to the fact that we have twist 2. Turns out that by playing similar games, one can derive a pairing for solutions of for operators of twist L. So for Baxter polynomials that describe operators of twist L. The result is the following. So the pairing, which I now have a lower index capital L that describe the twist, is now given by an integral that's now an L minus 1 dimensional integral. So recall that for L equals 2, this was a single integral. So I get one extra integral per twist. Here I add a binomial factor that's just an overall normalization and it's not important. But the crucial property is that this measure here, that defines the pairing between the two operators, is a factorized measure. So it's a product of 1 particle measures and 2 particle measures, and nothing more complicated than that. The 1 particle measures are just essentially the 1 over cosh squared we just described in the last slide. And the 2 particle measures are also given by some trigonometric functions that are quite simple. Crucially, there are no higher measures that couple 3 or more of the integration variables. Okay. Now, the reason to describe these 2-point pairings is that they turn out to be the building blocks for the structure constant. So, yes.
Sorry to interrupt. So,
No.
do you know, or does anyone know how to be more specific about the operators you're studying? So suppose do you know, or does anyone know how to be more specific about the operators that you're studying? So suppose I take, let's say, twist 4 operators. How many of them there are, and can you what are the derivatives?
You're asking if we can count the operators per spin at a fixed twist? The answer is yes.
Okay.
We can also write down their wave functions at their level and so on.
And the way your construction works, is it for each operator, I associate one of these functions that you're showing us, one of these keys?
Exactly. For each local primary operator in the theory, we have an associated Q function.
By primary, you mean super primary?
I mean primary, really. There are relations between two functions of operators that are related by supersymmetry, but yeah.
I see. Thank you.
I mean, in the context of the talk right now, I'm considering operators in the SL2 sector. So if you want, it describes also the other operators that are in the same supermultiplet, taking the highest weight representative as being this SL2 operator.
Right.
But really, this Q function should be in one-to-one correspondence with the operators in theory. And then can be systematically solved at the couple. Okay. So the reason to discuss these 2-point pairings, which I remind you, once again, are just bilinears in the, not bilinears, but they are functionals that each 2 Qs. And if they are different states, it's 0, otherwise it's a normalization. And these 2-point pairings are the building blocks for the structure constant. Now, let's describe what structure constant I'm talking about. So let's consider the simplest case of a structure constant of an operator in the SL2 sector with twist L and 2 BPS operators, half BPS operators, O2 and O3. Now, these half BPS operators are essentially given by some scalars in n equals to 4, contracted with some polarization vectors. So we have 6 scalars in n equals to 4. So this is a 6-dimensional vector that we require to be a null vector so that these operators have BPS. We insert L2 of these scalar fields for the operator 2 and L3 for the operator 3. And when we say the operators have BPS, in the language of these Q functions, we just have the statement that the polynomial, the Q polynomial is 1. Or in other words, it has no nodes. So that's just like the quantum harmonic oscillator we were describing earlier, right? The vacuum state, which has the lowest energy, the protected operator, has no nodes. It's like the vacuum. Now, what does the structure constant depends on? So it doesn't depend on the polarization vectors Y, or better saying, it does depend on it, but the dependence on the Y's is completely fixed by the R symmetry of the theory, by the global symmetry. So essentially, you can choose Y2 and I3 to point in any particular direction you want in this SO6 space. And once you do that, the structure constant will be given by a universal prefactor that depends on the Y's times a number. And then this number will then depend on, of course, on the Q function that describes the non-trivial SL2 operator, and on the sizes of the BPS operator, L2 and L3, as well, of course, on the size of the operator SL, non-BPS operator in the SL2 sector, which is the twist L. So here's a typical picture used to describe these structure constants. We have the non-BPS operator with size capital L, the BPS operator with size capital L2 and capital L3. At tree level, to compute these operators, all we do is we perform weak contractions of the scalar fields, and then we act with derivatives on the propagators, right? So we denote these classical propagators through these lines here. And then it's useful to define the so-called bridge lengths, which are these lowercase l's. So L12, we denote by simply by L, is the number of contractions between operators 1 and 2, and it's simply given by L plus L2 minus L3 over 2. And then similarly, we have L13 and L23, which we call L bottom. Now, having defined these kinematics, I can present the result for this Q function framework at the lowest order in the coupling. So at lowest order in the coupling, the result is simply that the structure constants are given by a very simple binomial factor, some factorials of spin, times precisely the pairings we were describing before, where in the numerator I have a pairing between the Q function of the non-BPS operator paired with the vacuum BPS Q function, with a pairing that is described by the bridge length L. So I remind you this lower index here essentially tells you how many integrals you have, right? So if L is say 2, we have a single integral as for the twist 2 case. And then in the denominator, we have a pairing between Q and itself on a pairing structure with index equal to the twist of the operator. Now, that such a formula should exist has been known for a really long time. I don't think it has ever been written as sharply as this, but it should have been done. And the reason is quite simple. It is that at the lowest order decouplling, meaning at tree level, all we are doing are performing weak contractions. And these weak contractions are just going to, so the structure constant is going to be about the combinatorics of these weak contractions. And it has been long known that the combinatoric of these weak contractions are precisely reproduced by scalar products in the spin chain that describes these operators. And scalar products in the spin chains that describe these operators have long been known to be given by these 2-point pairings I just described. So really the achievement here is just understanding in which prefactor we must put here in front to reproduce the tree-level structures. What is surprising though, and for that we have no reason to expect, is that there's a simple uplift of this formula to a quantum level. So at the next to leading order, the same structure constants are given by a simple promotion of these bilinear pairings and the promotion of this simple prefactor, where you say for the prefactor you just replace the spin by the spin plus g squared times the anomalous dimension of the non-BPS operator divided by 2. And then the measures are given by the same formula. So they're once again just the integrals of the product of the Q functions against a measure that once again is a factorized measure. So this survives to the quantum level. And it's corrected in a very simple fashion. So it's the tree level plus g squared times some simple trigonometric functions, both for the one particle measure and the two particle measure. As well as the Q function is no longer the polynomials that solve the now quantum corrected Baxter equation, but instead they are dressed by some simple functions. Here, H are essentially linear combinations of harmonic numbers evaluated at some positions that depend on the U parameter. And these Qs, Q1 and plus and Q minus are essentially higher conserved charges that describe this operator we're considering. So for example, Q1 plus is essentially just the anomalous dimension. And Q1 minus is a different charge. And if you want, in terms of the Q function, they are given by some simple log derivatives evaluated at I/2.
So these Baxter functions are exactly the ones that you get from the quantum spectral curve?
No. We do not understand exactly the relation between these dressed Q functions and those of the quantum spectral curve.
So what's the rule to construct these corrections, distressing?
So to the first correction to one loop or next to leading order, these dressed Q functions, they follow from the same orthogonality games we use to describe the pairings at tree level. So you start from Baxter equation, and from there you try to cook up a measure that makes the Baxter operator self-adjoint after some redefinitions. And once you assume, once you manage to construct this orthogonal pairing, they are exactly what show up in the structure constant.
What happens if you use the ones from the quantum spectral curve?
So when you say use the ones from the spectral curve, which ones do you mean? Because that may be a misunderstanding I have, but my understanding is that there are several Q functions that in a limit they reduce to say these Baxter polynomials, but it's not a unique uplift, right? I think this is correct, right? Is there a unique Q function that you would say is the right candidate?
Well, there's an hierarchy of Q functions, but I think at tweak coupling, yeah, I'm not sure. We can discuss this later.
Okay, I'm going
If I may add something.
Yes.
Sorry, if I may add something. Actually, you're correct, Alexandre. There is a series of Q functions, but there's not one unique Q function from the spectral curve. Like you get multiple indices which can be bosonic or fermionic, and then whatever you look at, these are like a lot. There are a lot of them. So there's not a unique way of doing it. You can take some asymptotic limits where you go to the ABA, and then you can probably get this Q polynomial in some sort of a combination with other functions, but there is not a unique Q function that you can think is the one that you would care about.
Yeah, I have a lot of time actually, so I can be more explicit about how we derive this next to leading order Q function for the case of twist 2. So for twist 2, the Baxter equation now at one loop, so one loop Baxter, it's corrected. It takes the following form. So in place of these u plus I over 2 squared factors, we now have Joukowsky variables, which are essentially some functions whose low energy, so low, weak coupling expansion is just one u plus. Well, let me be explicit. So this chi plus function squared, which is chi plus is essentially u plus I over 2 plus g squared times u plus I over 2. Maybe there's a factor 2 here or not. Times some function which I'll call b plus plus, which depends on the state. So I'll add an index 1 times q of u plus I over 2, or q plus I, plus the complex conjugate times the transfer matrix, which is now also corrected. Okay, now recall that in the three-level derivation, what was crucial was that the Baxter operator, which was essentially defined by the left-hand side of the equation, was a state-independent object. Now, this is no longer the case here because these B factors, they do depend on the higher charges of the operator. So what fixes this Q polynomial is essentially a redefinition. So Q tilde, as defined in the previous slide, which is given by just the Q times this exponential of the harmonic numbers, is essentially a transformation that makes the Baxter equation independent of the state. So Q tilde satisfies the simpler Baxter equation, which has no correction to the SYM matrix, essentially. So here I'm going to use plus plus to denote u plus I. Minus minus. Okay. Once you manage to recast, redefine Q so that you absorb these B factors, we now have a state-independent Baxter operator, and therefore we can play the same game you played at 3 level, with the difference that now, when we move the contours, we'll inevitably have to deal with poles. Because first, these chi functions no longer have double zeros at one loop, because we lose a factor. And also the Q functions themselves have poles at plus minus I over 2 that come from the harmonic numbers. So now the measure that we look for is no longer a measure with at most double poles. We can allow higher poles, provided the total contribution from all poles cancel. And when you require that this total contribution of all poles cancel, you precisely fix the measure to be what I wrote down here. So in summary, the principle that fixes this measure and is the form addressed Q function at the next leading order in the SL2 sector is orthogonality. Now, there are a bunch of comments I can make here, which are that we managed to obtain similar expressions in other sectors of the theory, even at higher loop orders than next to leading order. And there, even though at the 3 level, orthogonality is the guiding principle that fixes these Q functions and these pairings, at higher loops and in other sectors, orthogonality does not seem to be the correct principle. We managed to understand how to address these Q functions through alternative methods, but And even though orthogonality is still an important principle for some aspects of the problem, it's not the full answer on how to address these objects. Of course, at least not the most naive orthogonality principle. Perhaps one should reinterpret the measures we obtained for the other sectors in light of some orthogonality principle. That's not clear to us. So this is a bit fast, perhaps, but I hope it helps. Okay. So, any questions? Okay. So now let's focus at the next to leading order. This means order due to the 4 in the top coupling, or two loops. In a particular case of bridge length L equals to 1. So we do not have a complete answer for structure constants in the SL2 sector at this order, but for L equals to 1, we can say a few things. So recall that the formulas have been presented out of this forum, and we'll focus on the pink part here, which really is the part that captures the juicy dynamics of the three operators. You can think of this green part as essentially a normalization of the external operator, which you can perhaps compute from some other methods. But really, the juicy dynamics of the 3-point structure is in the pink part. Now, for L equals to I'll soon explain this picture, but for L equals to 1, turns out, as we described, this is a L minus 1 dimensional integral up to next to leading order. And for L equals to 1, this means it's a 0-dimensional integral, so it's just a constant. And in fact, in our normalization, this constant is just 1. So it's 1 to 3 level and 1 loop. So let me make a comment, which is that I told you that the structure constant depends on the bridge lengths small l and L13, which is essentially the twist, and also on this L bottom, L23. But of course, none of the formulas that presented so far depended on L bottom. It depended always on L and capital L. And the reason is that at weak coupling, this dependence on L bottom drops out. It shows up for the first time in the SL2 sector at 2 loops, which is next to leading order. And the result I'll present will have this dependence. And the result is the following. The result is that the simple factor of 1 at the 3 level and 1 loop becomes this at 2 loops. And here I emphasize a number of points. First, we had an L minus 1 dimensional integral up to next to leading order. And now we have this bunch of contact terms, which depend once again on these higher conserved charges of the operator, Q1 and Q2. And then it has a piece that's an integral of the Q function against some measure. The point here being that the number of integrals computing the structure constant increased by 1 at this order. And moreover, there is this eta parameter, which is 1 when the bridge at the bottom is greater than 1, and is 2 when the bridge at the bottom is equal to 1. So this result provides us with 2 very important lessons for this framework. The first is that as we crank up the coupling, we expect more and more integrals to show up. At least this is what is suggested. And this, of course, is sort of expected. There are other computations you can perform in this Q function framework of pairing Q functions and so on, that suggest that the number of integrals that appear in this formalism is associated to the number of degrees of freedom of the objects involved in the computation. And of course, as we crank up the coupling, in particular at finite coupling, we're really describing quantum strings that have an infinite number of degrees of freedom, no matter how short they are. They're no longer spin chains that whose number of degrees of freedom grow with the size, but really objects with an infinite number of degrees of freedom. So there is that. But then there is one very promising lesson that follows from that is suggested by this result, which is that the result for L bottom equals to 1 and L bottom greater than 1 is really of the same complexity and amounts to a small modification of the zeta parameter from 1 to 2. So why is this exciting? It's actually one of the main motivations to look for this Q function framework for structure constants. So to understand that, let's compare the computation we've performed so far with the canonical prescription for computation of structure constants in n equals 4 polynomials. So the canonical prescription is that we have three operators. The structure constant is described by the pair of pants in this way. And we want to compute this, essentially this sphere correlator with three insertions. And the way to do that in n equals to 4 is to cut this sphere correlator along these seams, these red, the blue, and green seams. Once you do that, of course, when you cut open this path integral, you need to insert a complete base of states that glue back together these two patches. These two patches we call, say, the front and the back hexagon patch. So this formula is I'm now describing is the so-called hexagonalization framework. And the idea is that once you cut open the worksheet, you decompactified it. And now what you have are excitations in the edges of the hexagon that live in this infinite volume space. And whenever you have excitations in asymptotic regions of an infinite volume space, you really have a scattering problem. And it's a scattering problem in a worksheet whose dynamics is integrable. And whenever you have a scattering problem in a theory whose dynamic is integrable, you can solve the scattering problem by means of the integrable bootstrap. That's what integrability does for you. So the way to compute structure constant is the integrability fixes each of these patches, which you then need to glue together by summing over a complete basis of states. Now, at weak coupling, this means leading order and actually to leading order. This sum over states along the seams on which you cut is projected to the vacuum state. The reason for that is that excitations along the seam, they have infinite mass at weak coupling, and so they can never be excited. More generally, the cost to propagate along these seams, so you recall that these seams here have some length, which is characterized by the bridge length, right? The total length is the length of the operator, but the partial length is the bridge length. And so if you have a very massive particle, it cannot be propagated long distances. So the amount that the cost for it to propagate is given by this Boltzmann factor, e to the minus e times the LB. Now, e to the minus energy, as I said, since the energy diverges at weak coupling, is something that's order g squared. And you see, therefore, that for larger bridge lengths, the cost to add a particle in this sum over states is suppressed for large LB. Now, for LB equals to 1, it turns out that this cost to propagate is g squared. There's another g squared that comes from being able to create this particle in the first place. And so the result is that at next to leading order, at g to the 4, you can finally first have an excitation in the sum over states along this bottom bridge here. And once you have this excitation in the bottom bridge, you need to sum over all its flavors and integrate over its possible momenta. So you see, at first you had a single sum over these two hexagon patches. And then at next to leading order, you need to also integrate over these hexagonal patches. So as soon as you start having these corrections of sum over states along the seam, the computational complexity of the hexagon framework increases significantly. So we have an extra integral when LB is small and particles can propagate. This is the main reason why the hexagon framework is very hard to use at high orders of perturbation theory, because you start having to sum over a large number of these mirror corrections, which are these corrections along these seams, and perform more and more integrals, and no one really knows how to properly address this problem efficiently. Now, what we are seeing in this Q function framework is that we don't see an extra integral in the Q function when we consider small l or big L. Or in other words, the computation that involves these finite volume effects is as complicated as the one that doesn't. Of course, what we've seen is just the tip of the iceberg. We've seen the first correction to linear decoupling. It's an open question whether this fact will survive to higher orders. But the fact that it works at two loops is very promising to us.
Sorry, Alexandre, can I ask you a question?
Yes.
So if you do this computation at the same order in the hexagon formalism, you still get one extra integral, right? So you get exactly the same number of integral. I don't see why, if you go, I mean, you would go to very high loop order to see multiple integrals. But how are you sure that even in your formalism, you will not see, for example, a G cube, something that it would be some sort of adjacent correction in your norm? Would you have something like this, or it would still be only one integral that has all this sort of, if you want, state sum altogether?
So let me see if I understand your question. Your question is whether adjacent wrapping will violate this rule I just proposed?
Yeah, I'm really curious to see that.
So we have not, so at the order G to the 4, there is no adjacent wrapping corrections, that's L2 sector. They start at order G to the 6. However, in the SU2 sector, it's not true. In the SU2 sector, we do have adjacent wrapping corrections at order G to the 4. And we managed to express arbitrary correlation functions in the SU2 sector to next leading order, including wrapping corrections. And the result is that the wrapping corrections, they do not affect the number of integrals. Both the asymptotic computation and the wrapping corrected computation are given by the same number of integrals.
Okay, I see. So this is your hope also if you try to do it in SL2, that in some sort of sense, the fact that you're correcting the Q function takes into account whatever this sum over state does. If I understand correctly, more or less what you get. Okay, I see.
Yeah, the wrapping effects derive the Q function, but they do not change the number of integrals.
I see. But then comes to like, what happens to the, like, this is sort of half wrapping. What happens when you have full wrapping? So do you think this will also be the case, or do you think it will not change in your formalism? I understand you guys maybe are not there, but it's just a curiosity. When I say full wrapping, I mean at 4 loops, you get this, finite size correction.
Well, I expect that there will be an enlargement on the number of integrals describing the pairings at this order. So I mean, of course, it's very hard to make such a prediction.
No,
but,
sure. I mean, of course, I was just curious if you guys have thought about it and was like, oh, maybe this happens or something like this, but it's fine, don't worry.
Yeah, there is some evidence that these wrapping corrections are related to an increase on the number of integrals, even in the full wrapping case. Now, on the other hand, here we've seen that the number of integrals increases also for the asymptotic computation, right? At next leading order, the asymptotic result started with just 1, which is 0-dimensional integral, and became a 1-dimensional integral. So this increase on the number of integral, even though it's expected from a wrapping perspective, it's not about wrapping. It's really about even the asymptotic result sees this effect. So I think that it's natural to be hopeful that the result with full wrapping will correspond to addressing of the Q function that's perhaps captured by the quantum spectral curve in some way, but will not make the pairings completely different.
Well, in our language, this is true because you are correcting the normalization with this Fredholm determinant, and in there, it is indeed true what you're trying to say. There is the normalization gets corrected by this wrapping effect. So what I'm trying to say is that I do expect that if you correct Q, you will be the same, but I also expect it to have more integral. Anyway, it's okay. I mean, I guess it's a future work. We'll see what happens. Thanks.
So talking about future work, I've got the conclusions, which is what I want to emphasize is that two results I did not have time to talk here, which are that, as I said, in a different sector of the theory, we have complete general formulas for next to leading order structure constants in terms of the Q functions. The story there is very beautiful. As I mentioned to João, it seems that the guiding principle there is not an orthogonality principle, at least not one we can see at least. But nevertheless, using alternative methods, we managed to develop this framework and express the structure constant as integrals of Qs. And with that, we observed that these small bridge effects, in particular when the adjacent bridges to the non-BPS operator are very short, they can be incorporated in the framework without making the computation more expensive. And for all of this talk, I've focused on the case of 3-point functions between one non-BPS operator and two BPS. We also obtained some structure constants for 3-point functions of 3 non-BPS operators in a formalism at the next to linear order. So then about future directions, there's the obvious question, which is, can we fix this structure to all loops? And how does it fit inside the quantum spectral curve? Can we interpret these measures and these dressings of the Q functions as some natural objects in the spectrum problem? And can we use the knowledge we have there to write down a all loop result? And then second, if not, can we bootstrap the problem? In a sense, are there some simple axioms that completely fix the structure of the structure, the form of the result, the measure, the dressing, the number of integrals, and etc. And of course, naively, we would think to the first two-loop order that this principle should be some kind of orthogonality between Q functions. And the third point is where we can construct an analogous framework for a direct computation of higher point functions in the spirit of the hexagonalization of Shotokumatsu and Thiago Ferri, where we would pair several Q functions corresponding to the external operators, integrate against a measure that captures the dependence on the cross ratios and spit out directly the quantum higher point function. And finally, the next point would be where the framework can be extended for arbitrary state operator. So we individually studied the SL2 sector and SU2 sector, having as guiding principle the rank 1 Baxter equations. The question is whether we can make the PSU2,2/4 symmetry of the model manifest and start on some covariant description of the system and then develop this framework. And finally, and perhaps most importantly, is whether we can use this framework to say something new about CFT and gauge theory by performing explorations that were not feasible with previous methods. So that's what I had to say for today. I have some extra slides on formulas for the SU2 sector if people have questions, but otherwise that's it.
Okay, very good. Let's thank Alexandre. Okay, a few minutes for questions if you have them. Could you explain what is the separation of variable in this setting? Like, what is I didn't see the use of that.
There is that you have this. So I think the word in separation of variables is really justified that at the weak coupling at the leading classical order, which is that we have this spin chain, which is a multidimensional Hilbert space, and we reduce the problem of computing the eigenstates and the correlation functions in this spin chain to this one-dimensional problem of solving this finite difference Baxter equation. And then once we have this Baxter equation, we are claiming that any structure constant or scalar product in the spin chain is given in terms of integrals of these Q functions that play the role of the separated variables wave function for this system. So essentially, the full state is described by factorized product of these Qs that you just pair them with these measures. In other words, this Q function reduces solving the system to a quantum harmonic oscillator-like problem, which is like a separated variables for the system. I don't have anything very deep to say about it in the quantum level, though.
Other question?
Yeah, about the last point, do you have in mind the complex spin and large spin? Or?
Yeah, for example, large spin would be a good call, right? Because one challenge aspect of the hexagonalization framework, which is the alternative method, is that at least the naive construction is that to compute correlators of operators with large number of spins, you need to have the sum over partitions, which grows exponentially with the spin. While here, the spin enters as an analytic parameter on the Q functions, and provided you have control of these integrals and of these Q functions at large spin, you could directly compute large spin structure constants and access this large spin physics from there. So in particular, yeah.
No, I was gonna say that actually, but in the one where actually it uses QSC objects, the one that with Ben and the other me and Arthur, you can actually access the large spin, because at the end the only point is that you should be able to solve the QSC at large spin, and this is a question that you can probably answer. I mean, you can do it in other regimes, but I guess there's nothing that stops you for solving the QSC at large spin and then plug it in and see what you get.
Right.
What about complex spin?
One could use this to study complex spin. In fact, I'm doing that. One question, of course, is whether this framework, which has been tested and at integer spin, where it gets modified at complex spin and where this modification is fixed uniquely, right? But yes, in principle, the framework does suggest that exploring complex spin is a good idea, because of course the spin is also an analytic parameter in these Baxter polynomials, which you can try to understand the complex spin that has been done in the past by Colli and others. And yeah.
Can you say some words about how to incorporate wrapping?
In the SL2 sector, in the SL2 sector, or
Either.
okay, so in the SL2 sector, that's what I try to describe in this slide here, which is that for bottom bridge equals to 1 at the next to next leading order, you have the first wrapping corrections where you have one particle flowing in this channel, right?
Right. But I mean, you just try to like change a little bit the dressing of the Q function in order to match data, or is there something?
It was more direct because it was a simple recognition that, so we first did asymptotic result with no wrapping, and we saw that f equals equal to 1 and given by this integral. And then this integral, if you open the paper by Basso, Pedro, and Shota on the three-loop wrapping, you will just immediately recognize this object. Sorry, even in the original hexagon paper. This formula is essentially written exactly like this in their paper. So you just look at it and realize that you just need to shift factor of 2 to incorporate wrapping.
Okay.
In this case, it was a bit too easy. In the SU2 sector, it's a bit more involved. So it's a bit of a long story, but I can try to summarize. Which is that in the SU2 sector, you have adjacent wrapping at two loops. However, this adjacent wrapping is so that whenever it's present, the structure constant vanish. But it only vanish once you take into account the wrapping corrections. The vanishing of the structure constant can be understood from group theory. And essentially reproducing the zeros of the structure constant fix the dressing of the Q function in the case you have wrapping. So in particular, what we want to look for is the case in which one of the adjacent bridges is equal to 1. You see, let's look at this numerator here, which is essentially the DVD amplitude. For L equals to 1, and spin greater than 2, so greater or equal than 2, which means physical operator, this binomial immediately vanish. And so we have manifest the fact that the structure constant vanish for L equals to 1. Now you can try to ask whether the structure constant will vanish in the case in which L is given by capital L minus 1, so the right bridge is now 1. Of course, the result should be symmetric under this. L goes to L minus 1. L, which is equal to 1, goes to capital L minus 1. And the claim is that to recover this symmetry, you need to add to the dressing of the Q function this factor, which is in blue here. Yeah, sorry. This factor that has this delta function here. So when L equal to L minus 1, you dress the Q function. So you see that the Q function is dressed by this B factor. Precisely when you have dressing, when you have wrapping. And once you include this factor, which is a function of the charges of the theory and some function of the Joukowsky, you recover the wrapping result.
I see. This is really begging for a bootstrap.
Yes. There's a nice it's really too long to explain here, but I think it's well explained in a paper, which is that the method used to derive these formulas from in the SU2 sector is the following. First, we start with the obvious realization that at tree level, all we are doing is computing scalar products in the spin chain. And these scalar products can be written in terms of the integrals of the Q function, not only for the spin chain of n equals to 4 spring mills, but also in the case of the inhomogeneous spin chain. So you start with an expression for the scalar products of the inhomogeneous spin chain in terms of Q functions. Now, up to 2 loops in the SU2 sector, the S matrix does not receive corrections. And all the quantum effects do for the SU2 system is to correct the propagation of the magnons on the spin chain. This propagation of the magnons correction of the propagation of magnons can be mimicked by properly tuning these inhomogeneities, or in other words, by acting with a differential operator on the inhomogeneities. This is the idea of these theta morphisms that Pedro and Collier considered at 1 loop a long time ago. So we understood that we can generalize these theta morphisms to 2 loops.
Mm-hmm.
These theta morphisms, though, it is sensitive to whether you are in a closed chain or in an open chain. And really, you should think about the DVD amplitude as a scalar product in an open chain. And in the open chain, the theta morphism has boundary effects. And these boundary effects have some range that grows with the coupling. And you see that this growth of the range is irrelevant for the absolute value of the structure constant to the first 2 orders. But at 2 loops, this range is big enough that it affects the form of the structure constant when the bridge is too big so that you reach the right boundary. So precisely when the L is super big, so L minus 1, it's almost the size of the operator, then you get affected by these boundary terms of the theta morphism, and they generate this factor that properly restores symmetry and reproduce wrapping corrections. I know
See.
it was probably quite fast, but that's the general idea, and have lots of details in the paper.
Thank you.
Yeah.
There's a question in the chat. The question is, are the three non-BPS operators you are referring the abelian ones, or can you write a formula for more general correlators also?
It's for the abelian cases. So we have formulas for three non-BPS operators in the SL2 sector, when two of them have parallel polarizations and one of them is orthogonal to the other two. That's the result we have. So this connects to the question by Vasco about large spin. Suppose we can generalize this non-BPS formula to something that incorporates all possible polarizations and therefore provides this even at the tree level or at one loop, or actually hopefully at one loop, for this general polarization structural constants of spinning operators. Then solving for these Q functions at large spin should be something relatively easy, right? And through our previous works, Vasco, we could then use these results to express the dynamics of the Wilson loop directly through the structural constants. So that will be one way about learning more about gauge theory from these formulas.
Okay, very good. Any other questions? Okay, if not, let's thank Alexandre once again.
Thanks.
And we will stop here. Okay, thank you, Alexandre.
Thanks.